How do you rank reasoning models? The standard way is to run each model once per benchmark question and read off a score, but reasoning models are stochastic. Ask the same question 80 times and you get 80 different answers. So a 2026 paper from Case Western Reserve asks the obvious question: which ranking rule should you use on all those trials, and does it even matter? They tested 72 ranking methods, 20 models, 4 Olympiad math benchmarks, 80 trials each. The answer is quietly uncomfortable for every leaderboard you have ever read. Here is the problem. Test time scaling turns evaluation into a repeated sampling problem. There is no single, the score. For each model on each question you draw n independent samples, and you get a binary outcome tensor, 20 models, 30 questions, 80 trials. That tensor is the raw object. Now you have to collapse it back into a ranking. And there are dozens of ways to do that. Bradley Terry, Borda, PageRank, ELO, TrueSkill, pairwise, pointwise, listwise. The paper's library implements 72 of them. The scary question is whether they all agree. The reference ranking, the gold standard, is the Bayesian posterior mean estimator with a uniform prior evaluated at the full 80 trials. It is order equivalent to mean accuracy. Then every other method gets measured by how well its full trial ranking agrees with that gold standard, using Kendall's tau. Tau of 1 means identical ordering. Tau of 0 means no correlation. The setup is clean. 72 methods, 1 tensor, 1 yardstick, and here is the first result. At the full budget of 80 trials, most methods agree with the gold standard. The mean Kendall tau is between 0.93 and 0.95 on each benchmark, 0.962 combined. On HMMT 25, 34 of the 72 methods recover the exact ordering. At high budget, the choice of ranking rule barely matters. Read that twice. At high budget, leaderboard rankings are stable, but shrink the budget. Drop to a single trial per question, which is what almost every public benchmark actually runs, and the picture flips. The best methods reach tau around 0.86 on the combined set. But on the hardest benchmark, HMMT 25, no method beats 0.79. The model ranking itself becomes genuinely uncertain. And look at the models. Quen 3. Thinking dominates every benchmark, while Bespoke Stratos sits near 0 on HMMT. One trial, and the field collapses into noise. Picture the difference. A single trial benchmark is one finisher crossing one line, a snapshot that pretends to be the whole race. Repeated sampling is the whole field spread across the track, 80 attempts showing the real distribution of where each model lands. That distribution is what every ranking rule is trying to summarize. And different rules summarize it differently. Now, the most actionable result. The paper's practical trick is a greedy prior Bayesian estimator. You run one cheap greedy decode first and use it as an informative prior. That always cuts the variance of single trial rankings by 16 to 52%. The biggest win is on Brumo, 52%. But there is a catch. The greedy prior is biased. On the hardest benchmark, it actually shifts the mean ranking in the wrong direction, minus 0.022. Lower variance, but a biased center. You cannot just take it for free, so the practical recipe is clear. Use the uniform prior Bayesian estimator, Bayes-U, as your default. It is safe. Only reach for the greedy prior if you have first checked, on a pilot, that greedy decodes and sampled decodes produce the same ranking on your data, and remember the theoretical warning. The Bradley-Terry ranking and the average accuracy ranking are not guaranteed to coincide. The paper constructs the smallest counterexample at just 8 questions. The choice of rule is not cosmetic. 72 methods, 20 models, 4 benchmarks, 80 trials, 7,400 GPU hours. At high budget, the ranking rule barely matters. At low budget, it matters a lot, and the greedy prior trades bias for variance. The paper is Ranking Reasoning LLMs under Test Time Scaling. The Scorio library is linked below. The lesson generalizes. Every single trial leaderboard you have ever trusted is one draw from a distribution. Subscribe for the next breakdown.